I might now invite again Dr. Josef Trögl to present about the water purification using photocatalysis, electrocoagulation, cheap sorbents, and encapsulated bacteria. Very specific presentation about technological process. The floor is yours.
Thanks again. Let me share the screen. Can you see the presentations?
Yes. I see the first slide.
Yeah. So in fact, we discussed that you are lacking one more member. So I on this conference. So I propose to summarize a bit our previous research and possibilities, which in fact we currently continue on with the pharmaceuticals. So I will go through it a little bit more quickly with some examples of previous published results.
Yeah, thank you very much. We are a little bit running out of time. Then, if you could.
Yeah, I will go on quickly.
Little bit.
So, as Faculty of Environment, we focus a bit on water as well, of course, including the wastewater treatment technologies. But I would like to speak about a little bit of non-conventional sorbents, photocatalytic oxidation, and biological treatment and electrocoagulation. I will start with the non-conventional sorbents. This is a long history research here on our faculty around Professor Janosch, who also proposed me the work on our faculty 15 years ago. What they were initially researching sorption of different pollutants on many waste materials such as fly ash, spent sawdust, or modified materials. Also modified nature materials such as metallic humates from cheap coal, or more recently graphene composites which have high sorption surface. And the most recent research is on let's say artificial sorbents based dominantly on metallic oxide, and especially on cerium oxide. Professor Janosch loves this part of periodic table, the lanthanoids, so he likes to work with cerium oxide, and it has got a lot of interesting properties. And also quite recent research has been focused also on practical modifications such as preparation of magnetically separable sorbents which have the reactive part and magnetic core, or hydrophobic sorbents and things like that. Really the latest specialty of this team are the reactive sorbents. So it's not just sorption of the material, but the sorbents provide some form of catalytic properties. It's not always pure catalysis, yeah, but generally yes. And especially the cerium oxide can provide catalytic properties on organophosphate compounds. These are quite toxic. You may know them either as pesticides, such as parathion methyl, or also the chemical warfare agents such as soman, sarin, tabun, and these highly toxic compounds. So these cerium oxides are capable of decomposing of these organophosphate materials, which you can see here on this sample chart. You can see that the elimination is quite fast, and we get to almost 100% conversions after like 2 hours. Here you have some examples with the real nerve agent, soman and VX. This research was carried out with the help of the Military Research Institute. We really don't work with someone here in the laboratories where students have access. That would probably lead to an undesired loss of students. What is also interesting that these materials can interact with, let's say, standard biochemical compounds such as adenosine triphosphate, DNA, etc. Nevertheless, it has not much to do with wastewater treatment, so I just leave it here as a sample. Photocatalysis was introduced about like 10 years ago. I mean, here in our faculty. Otherwise, it's quite a known process. Even currently, there are marketed products such as the titanium oxide-based paintings on wall, which provide also the photocatalytic activity, so that the painting does not get as much dirty during time. It has self-cleaning properties. Nevertheless, what we focused dominantly on here was the homogeneous catalysis. I try to use some form of pointer, and homogeneous catalysis, homogeneous photocatalysis is not as much established. The most positive thing on this is that a lot of homogeneous photocatalysis work in standard visible light. They, unlike the titanium dioxide, which requires generally the ultraviolet light, more energy and less safe, these homogeneous photocatalysis can work under visible irradiation. Our research went like into two main directions. One was on using microreactors, which enable study of the exact mechanism of the decomposition. On the other hand, we collaborate a lot with the industry, so we have also the semi-pilot scale, or maybe quarter pilot scale reactor that can be used for the real water, real polluted water purification. Here you can see our so-called photo bench with the photoreactor, where you can really precisely set all the properties starting from the wavelength of the light, the different filters, intensity, temperature, oxygen, no oxygen, all you need here. And just few examples of results. Dominantly, the research was carried out with these phthalocyanins, which are tetrapyrrole-derived compounds. They are by structure similar to many, let's say, nature-based compounds such as chlorophyll or hem as a part of hemoglobin, our blood dye, and so these compounds can be found in nature. Nevertheless, these phthalocyanins are modifications, so they are not nature-based, and they have very much interesting properties. Especially they are non-toxic and they are quite cheap. Some of them are even used as a textile dyes, for example, for the blue jeans. This is very popular. So here you can see some sample of results. So this is hydrogen peroxide UVC elimination of chlorophenol using also this phthalocyanins as a photocatalysts. Here you can see the dye, how it looks like, the molecular model, and you can see that it really works quite well and again quite fast. Chlorophenols were provided, or the chlorophenol polluted water was provided by the Deconta company as the real wastewater from their one of their processes. And now a little more about my spot of.
I am very sorry. 2 minutes.
Okay. Immobilization of microorganisms leads to many positive effects. Nevertheless, it also leads to some more costs. We are like nature inspired because microorganisms in nature tend to immobilize themselves, for example, to biofilms. And probably the most positive on the artificial immobilization is the protection, so that the immobilized microorganisms then can work in environment that is somehow more hostile for them, such as toxic or highly saline. So in this case, I will show you just our results, which we carried out together with the Lenticats company. However, this one does no longer exist. It was sold, but the technology exists. And it was focused on the wastewaters from the sulfuration plants from the coal power station. So we had water which was lacking almost phosphorus, was very highly saline, and lot of nitrates and nitrates, lot of COD organics, but not much degradable. So here you can see that we have successfully established long-term continuous experiments that provided quite high denitrification activity and could be used for this form of treatments. And as final electrocoagulation, it was mentioned here by one of the speakers as well that it's applied. So electrocoagulation, in fact, is a form of substitute to standard coagulation methods that are often used in water purification system. The positive thing is that generally you don't need as much chemicals to put into the water because they are partly substituted by the electrochemical reaction, which you can see here on the comparison. Here is our semi-pilot scale or quarter pilot scale reactor for electrocoagulation. We have tested different applications, and as one example, these were again the real wastewaters with lot of different toxic metals that were successfully treated this way. Again, I think in collaboration with the Deconta company, which is one of the biggest companies focusing on decontamination. Again, we would be happy to try new real applications with new partners, and thank you for attention.
Josef, thank you very much for your presentation. As I do not see any questions in the Slido, I would leave the potential questions for the bilateral communication via email or telephone calls. Thank you very much for your technical knowledge.